Hello, I'm Ezra. This is AP Calculus AB and BC Review, Unit 7, Differential Equations. In this unit, we go over modeling scenarios with differential equations. We look at slope fields and how to recognize slope fields of different functions, as well as how to draw them. We figure out how to solve differential equations using separation of variables. And then for the BC only topics, we have Euler's method, and then we take a look at the properties of logistic differential equations. So let's begin. So how would we model a scenario with a differential equation? Well, first you have to define what a differential equation is. So a differential equation is an equation with a derivative in it. Derivative. So, what does that mean? Well, it means that the derivative of some variable, or what we're going to say is the rate, is directly proportional to itself. So, for instance, here's a very simple one. K is some sort of constant. We're going to use K as our constant here. So, this is a differential equation because the rate of change of y with respect to time doesn't change depending on time, but it changes depending on y. So when y is 3, the rate of change with respect to y is higher than when y is 1. The time does not matter. So, how do you model a situation with a differential equation? Well, you'll get something such as a question saying that you have a scenario where the rate of change of temperature in a cup of coffee is directly proportional to the temperature in the cup of coffee. So, we're going to say dC for Celsius over dt with respect to time. So when it says the rate of change of the coffee, the temperature in the coffee, is directly proportional to the temperature, we're going to say that K is what we call a proportionality constant. So basically, this is just going to be any constant that will model the scenario. So it doesn't matter what this is, and if you see it in multiple choice questions, it's just going to be left as K. So if it is proportional to the temperature, C is our temperature here, that just means that the derivative of C with respect to time is equal to the temperature times some sort of constant. Now, if it says the temperature of the coffee in the cup of coffee is inversely proportional, that means that the temperature is inversely proportional to this constant, this proportionality constant. So that means your temperature is on the bottom. Inverse means 1 over the variable in this case. So if you had it inversely proportional, so you put your proportional constant, and then inversely means that you have it over the variable. And it can get more complicated than this, but it doesn't get that much more complicated, if that makes sense. So, for instance, it can say that V naught is the original volume, or I'll just say D, or E is the original volume in a tank of water. And then V is current volume. So, an equation, a differential equation, it can ask you it will say, what equation represents the scenario where the rate of change of volume is proportional to the difference between the original volume and the current volume? You would say the change in volume with respect to time is proportional, so you have your K, proportional to the difference between the original volume and the current volume. So you would have this. So that means if you think about this conceptually, this volume is going to go down because you have an original volume and you're losing volume. Or actually, in this case, depending on the constant, you could be gaining or losing volume. But this models the scenario because you have the difference between the total volume and then you have the current volume. Or if it said, for instance, it was inversely proportional to the difference between the original volume and the current volume, you would have your constant over original volume minus current volume. So that is, simply put, how you model scenarios. And when you look at FRQs, usually you will be given some sort of function that will model the scenario. On MCQs, you could be given a function or it can ask you to find a function that models this scenario. Anyways, now we're going to talk about slope fields. So these are always written as dy over dx. You're using the variables y and x equals some function, which we're going to talk about. But basically, it is a collection of lines that show the slope at certain points. So if you have x plus 1 over y plus 1, this is like your slope field. If you want to find the slope at any given point, you plug in the numbers of that point. So if you wanted to find the slope at 1, 1, you plug x equals 1 in, and you plug y equals 1 in. So you get 1 plus 1 on the top is 2, 1 plus 1 on the bottom is 2. So then at 1, 1, the slope is going to be 1. So your slope field, you will draw a slope of 1. Let's say at 2, 1, all right, plug 2 in for x, you get 2 plus 1 is 3. Plug 1 in for y, 1 plus 1 is 2. Then you get 3 over 2 as your slope. So at 2, 1, you're going to have a steeper slope of 3 over 2. Now if you go negative, x equals negative 1, y equals 1, you get negative 1 plus 1 is 0, 1 plus 1 is 2, so 0 over 2 is 0. So at x equals negative 1 is going to be 0. And this is true for every single negative 1 value, because at x equals negative 1, it doesn't matter what the y value is because on the top it's 0. Except at y equals negative 1, you won't have anything because negative 1 plus 1 is 0, and anything over 0 is undefined. So, what is a pretty commonly asked question on an FRQ is you are given a graph, and then you are given points like 0, 1, 0, 2, 0, 3, 1, 0, 2, 0, or 0, 1, what am I saying? 1, 0, 1, 1, 1, 2, 1, 3, and then 2, 0, 2, 1, 2, 2, 2, 3. You're given like 12 points like this, and it will give you an equation. dy over dx equals x squared plus 1 over y plus 1. All right, so plug in some values here. At 0, 0, the slope is going to be 0 squared plus 1 over 0 plus 1, which is just 1. So at 0, the slope is going to be 1. Okay, at 0, x equals 0, y equals 1, it's going to be 0 plus 1 over 1 plus 1, so that's 1 over 2, so the slope is going to be smaller here. And then you can do the math, but basically you plug in for every single point. At 0, 3, you have 0 plus 1 over 3 plus 1, which is 1 over 4. All right, let's move on to this next column. 1, 0 is going to be 1 plus 1 over 0 plus 1. So 1 plus 1 is 2, 0 plus 1 is 1, so the slope here is going to be 2. And then at y equals 1, it's going to be 2 over 2, so it's going to be back to this. And then at y equals 2, it's going to be 2 over 3, so it's going to be slightly less than 1. And then it's going to be 2 over 4, so it's going to be 1/2 up here. And then, let's look at 2. X equals 2, it's going to be 5 over 1. So the slope here is super steep. It's going to be 5. And then at 2 comma 1, it's going to be 5 over 2. And then at 2 comma 2, it's going to be 5 over 3. And at 2 comma 3, 5 over 4. So any of these slopes, if you wanted to find the slope at any given point, you just have to plug in the points into the differential equation it gives you. Now, it will also sometimes ask you to find the solution curve of a function. So a differential equation can pass through any point, and it will usually give you this point. Because, remember, the derivative of a constant is 0. So if you have a dy over dx equals some function with x and y in it, once you integrate, you can have any constant added onto that. So when you take the derivative, it goes away, if that makes sense. So this function can pass through any of these points. It will tell you, find the solution curve through the point 1 comma 2. Alright, so find the solution curve through this point. All you have to do is sketch a curve, which I'm going to do in red, through that point, using the slopes over here. So it will look something like that. Or if it says go through 1 comma 0, well, then it will look something like this. It will look different than the curve from up here. Finally, with slope fields, it will ask you to recognize slope fields. So here is a common one that it will give you. You have this, and then you have and then usually recognized slope fields will be on multiple choice questions. Like this. So how would you recognize this slope field? Well, it will say which one of these differential equations models this slope field. So you'll have dy over dx, and in this case, I drew 1 over 1 plus x squared. How do I know this is 1 over 1 plus x squared? Well, first you have to integrate this. Now, when you integrate this, you can move this dx over to this side. So you get dy, this is a little taste of separation of variables, dy equals 1 plus x squared dx. And then when you integrate both sides, you have y equals arctan of x plus c. So if you know what arctan of x looks like, which you should, arctan of x looks like this. Okay, so if you modeled the slopes here, as x approaches both negative infinity and positive infinity, eventually this slope goes to 0, which makes sense with what we see over here. So that's how you would figure that out. One more that you can look at is a function that looks like, well, I would make the graph like this. Something like this. And now, if you look at this, you instantly are going to think it's a sine function, and you would be correct. You will have dy over dx equals cosine x. And then what is the integral of cosine x? Sine x. So you have y equals sine of x. And then, over here, it will still look like a sine function. So usually, these slope fields that you get, these are always on multiple choice again, will look sort of like the function that it represents, even if it's dy over dx. So, if you have some sort of one that looks like this, then you can already recognize that it is a trig function. If you, for instance, have a function that looks like this, you can think that this is an exponential function. You should automatically be thinking that. if you have one that looks like this, this is going to be a 1 over x squared plus 1 function. And then, finally, anything that looks like this, where you have 0 slope at the center, will be some sort of quadratic. As well as this, you can recognize slope fields of weird functions. So it won't always give you some regular function like x squared or cosine of x. Sometimes it will give you x minus y over x squared plus 1. So here, when x and y are the same, the slope is going to be 0 no matter what. So you're going to see like a 0 line of 0 slopes going on the line of y equals x, because again, when x and y are the same, then the slope will be 0. So you have to look for these sort of relationships. And then you have x squared plus 1. This means that there will be no undefined points in the function, and it also means that going left and right, the slope will decrease. So even if you have -1, -2, it's always going to be less as you go forward in x. So if you have x equals 2, y equals 0, you have 2 over 5. So you'll have something like this. And then if 3y equals 0, it's going to be even less, and eventually it's going to look like 0. So looking at the function, it will give you like this function, which slope field represents this function. You want to look for key components of this function, such as x minus y being 0 when they're the same, and the x's getting smaller, or the slope getting smaller as x goes on. So there will always be 1 to 2 slope field questions on a test as well. Okay. Finally, for the AB topics, and probably the most extensive, is solving differential equations with separation of variables. So as I mentioned before with the arctan, you can have a dy over dx, and you can move the dx over to the other side of the equation. So what happens if I give you one like this? Now you have a dy and you have a dx, and then you have this portion over here. So if I move the dx over here, that's not going to do anything. You can't integrate y with respect to x. So how do you integrate this? How do you solve? Well, what you do is you divide both sides by 1 minus y, and then you times both sides by dx. So what you end up getting is you get dy over 1 minus y equals 3 times dx. So let me repeat. You move all of your y terms, your 1 minus y, you divide them over, and then you multiply your dx over, so you have dy and dx separate. So all of your y terms are on this side, all of your quote-unquote x terms and constants are on the x side. So now you can integrate this. And then, using u sub, or just in your brain if you're already good enough with integrating like that, you'll get negative ln 1 minus y equals 3x plus c. This is important. C will always be on the x side and not on the y side. So do not add a plus c onto the y side, only add it to the x side. So now we have to simplify this. You can move the negative over, but don't put the negative into the plus c. The c absorbs all constants and all numbers added to it. So negative 1 is a constant. So this just becomes negative 1 minus y equals negative 3x plus c. All right, how do we get rid of this ln? You take e. So e crosses that, e crosses that. So 1 minus y equals e to the negative 3x plus c. Okay, we can simplify this further, though. This is not simplified because we have e to the negative 3x plus c. So if you have something like e to the a plus b, this is the same thing as e to the a times e to the b. Or that goes for any like multiplication constant. So this is the same thing as saying e to the negative 3x times e to the c. But again, like I said before, the c absorbs all constants. So e to the c is actually a constant here. So this e to the c can just be rewritten as c, and then that can be put in the front. So now we have c e to the negative 3x. Now we just have to simplify, move this 1 over, move the negative over. You will get 1 minus c e to the negative 3x equals y. This is your solution for this differential equation up here. This is your general solution. So when it says to find the general solution, you will have a constant c somewhere in your answer. Now, another thing it could say when x equals 0, y equals 8. This is called an initial condition. So now you have to use this relationship and put it into this function. So let's do that. 1 minus c e to the negative 3 times 0. I'm just going to write that as 0 equals 8. E to the 0 equals 1. So in other words, 1 minus c equals 8. And then that means c equals negative 7. We've just solved for this missing constant c using the initial condition. So moving this to the side, now we can rewrite it as y equals 1 plus 7e to the negative 3x, and this is our specific solution depending on this initial condition. So I'll reiterate. General solution, specific solution, depending on this. All right, so I'm going to give you a real world problem, not necessarily like giving you the details of it, but this is a problem that you would 100% see on an AP. So it says that some sort of scenario is modeled by the function dy over dt equals 10 minus y over 10. And then it says at t equals 0, y equals 120. Okay, how do we model this? Well, here you might notice that you can't really move this over. If you move it over, you get y over 10 plus dy over dt. When you try to multiply this dy over dt to get it out of the denominator, you will have y over 10 dt plus dy equals 10 dt, which doesn't mean anything. You can't integrate this. So first step, you will have to separate this into a distinct constant and a distinct y. So we have to multiply this whole thing by 10, essentially, or you're factoring out a 10. So, or you're really factoring out a 1/10 because you're multiplying it by 10. So you have 1/10 times 100 minus y. These two things are equivalent. You are basically taking this 1/10, multiplying this thing by 10, and then multiplying this by 1/10, if that makes sense. So the inside gets multiplied by 10, and then you add a 1/10 on the outside, so it like balances it out. So you don't have the same thing, if that makes sense. These two functions are equivalent. So now we can separate. So we have dy over 100 minus y equals 1/10 dt. We move this dt over here. We move this 100 minus y to the bottom, and now we have this. And now we can integrate. So now we have negative ln 100 minus y, which equals 1/10 t. I'm going to write it like this. So I have my plus c. Now again, we move the negative over. We do not put it into the c. So we have ln 100 minus y equals negative 1/10 t plus c. Okay. Now we're going to do what we did before with the e, canceling these out. E. Okay. E to the negative 1/10 t. And remember, this plus c that we have up here can be moved down in front of the e because it's a constant. So ce to the negative 1/10 t equals 100 minus y. We're close to solving it. We have y equals 100 minus ce to the negative 1/10 t. General solution. Now, we take that general solution and bring it up here. So, y equals 100 minus ce to the negative 1/10 t. At t equals 0, y equals 120. So, 120 equals 100 minus c. ce to the 0 is 1. So it's 100 minus c. Therefore, c equals negative 20. And then our final solution is y equals 100 plus 20 e to the negative 1/10 t. This is our specific solution for this scenario. On an FRQ, which you will very likely have a separation of variables on an FRQ, this is literally half the points. Doing this step, separating your variables, finding the correct integrals, finding your general solution, plugging in your C value and getting your specific solution. That is half the points on the FRQ. So if you don't know how to do this, you need to study up because it is very important. So now, we are going to go on to the BC only topics. So we have Euler's method. So Euler's method, in essence, is just repeated tangent lines on top of tangent lines. So it is, again, back to tangent line approximation, except this time we're getting even more accurate. So let me draw some curve over here, right? If you wanted a tangent line, I'm trying to get a nice curve, a tangent line from here to approximate this point, right? This tangent line wouldn't be too accurate. What Euler's method does is it takes this tangent line and then goes halfway between this point and this point on this tangent line, and then from here creates another line tangent to the graph, tangent to this graph, but it's on the tangent line. So then, when you're looking at this approximation, it will be much more accurate. So let's look at how you would do that. So, take an equation, dy over dx equals 4x plus y. So dy over dx is our slope. M equals slope is this, which you need to know. So then, if we have our initial condition, which is x equals 2, y equals 0, you want to approximate what x equals 3, like what the function is at x equals 3, with 2 steps. This is how it will be written on the AP test. You do not need to figure out that you need to use Euler's method. It will tell you very specifically, using Euler's method, find this using this amount of steps. So what is a step? Well, we're going to draw a table. This is what I always like to do. So, in this table, we will mark out our conditions. So we have 2, 0 as a point. So x equals 2, y equals 0. And now dy over dx is this. So we plug in 2, 0. 2 goes into here, 4 times 2 is 8, 0 into here, 0. So dy over dx is 8. Now we do our tangent line approximation for x equals 2.5. Because remember, we're trying to find when x equals 3, y equals what? Using an approximation. So y minus 0, so we're not even going to write it, equals 8 times x minus 2. So since x is 2.5, it's just going to be y equals 8 times 0.5, or y equals 4. So put that into your table. Now, move this up here. You need to show your work for all the tangent lines in order to get the points. So 2.5 and 4. Now we plug this into our formula. 4 times 2.5 is 10. 10 plus 4 is 14. So that means dy over dx is 14 over here. So now let's write again. Y minus 4 equals 14 times x minus 2.5. And again, since x is 3, y minus 4 equals 14 times 0.5, because 3 minus 2.5 is 0.5. So that means y minus 4 equals 7, y equals 11. So at x equals 3, y equals 11, using Euler's method. It's quite a few steps, but this, again, is always one question on the BC test. Whether it is a multiple choice or on the FRQ, you will always see it at least once. So knowing how to do it is important. Okay, we're going to do one more Euler's method. So we're given dy over dx equals 1 over x plus 2. Okay, starting at 0, 1, find y of 2 with 4 steps. So this is going to be quite a long and annoying one. So, as always, make your chart. This will be helpful. 0, 0.5, 1, 1.5, 2. And I'm going to move this over to here. So, okay. At 0, we know it's 1. X equals 0 into here. The slope is going to be 1/2. Okay. So, y minus 1 equals 1/2 x minus 0.5. Alright. So, x minus 0.5, you plug in, or x minus 0, really. You plug in 0.5. 1/2 times 0.5 is 1/4. That means y equals 1.25 over here. Okay, now x equals 0.5 into here. 1 over 0.5 plus 2 is 1 over 2.5, which is 2 over 5. Okay, y minus 1.25 equals 2 over 5 x minus 0.5. So since these are all 0.5 steps, then we can just put 2/5 times 0.5. So 2/5 times 0.5 is 2/10, which is 0.2. And then y minus 1.25 equals 0.2. Y equals 1.45. Now, plug 1 into here, you get 1/3. So over here, it's 1/3. And I'm going to move all this up because it's getting to be a lot of writing. So y minus 1.45 equals 1/3 times 0.5. So now you have y minus 1.45 equals 1/6. So 1/6 is about 0.167, I believe. So then y equals 1.45 plus 1.067, which is going to be 1.617. Yes. Okay. 1.617. Now we have 1.5 plus 2. So 1 over 3.5 is going to be 2 over 7. And then I'm going to move this up again. And then we have y minus 1.617 equals 2/7 times 0.5. And then finally, you get 2/14 or 1/7. So then 1/7 is about like 1.412. Or 0.412. And then you add that to 1.617. And then you get 1.759. So 1.759. That is y of 2 with 4 steps. So it's never going to give you something this complicated or this long, but you just need to know how to do it. Sometimes it can give you 4 steps, sometimes it can give you 3. It's never going to give you more than 4 steps, but usually it will be 2. Okay, so now that was Euler's method. Finally, we're going to look at logistic differential equations. So, what is a logistic differential equation? Well, it is one where the equation essentially plateaus at a number. So, it grows, and then it slows down its growth and eventually plateaus at a number. So, this can be used to model a whole bunch of things. Very often it's used for stuff like population. Because eventually populations of animals are going to go to a steady number and kind of hover around that number. So how do these equations look? Well, in differential form, you're going to see dy over, let's say, dt equals k times y times L minus y. So what is this? K, constant, like we said before. And then L is what is called the carrying capacity. So this carrying capacity is, if you were to write this as a normal function, like this, the carrying capacity is what this value caps at. So if L is 50 in this case, then this value right here would be 50, and L would plateau, or the function would plateau at that L value, which is 50. So, written in function form, you can separate the variables here, and it's a whole long separation of variables, and you won't have to do it on the test, but this in normal form will be y of t equals L over 1 plus c e to the negative L k t. So something very long. So again, this is carrying capacity. This is our proportionality constant, and then this is our constant of integration. How do these functions behave, though? So there's a few things you can be asked on the test. So one of them is to find the rate at which, y is changing when it is changing at the fastest. So if you have this function, the slope of the function maxes out at around here, at this x value. So I'm going to call it x1. So what is this x value? How can we find it? Well, it is easier than you might think. This x value is just half of L, or the y value is just half of L, not the x value. So the x value, you won't ever need to know, because if it asks you the slope when it is increasing at its maximum, you already have your slope. You don't need your slope in terms of x, or in terms of t in this case. You have your slope in terms of y. So if your carrying capacity is 50, then you just do k times 25 times 50 minus 25, because half of 50 equals 25, and then when y is equal to 25, this increases at a maximum. So a problem you can get is find dy over dt when it is at its maximum. All you do is find L over 2 and then plug that back into your equation and find your dy over dt. Finally, we're going to talk about concavity here, because another problem it can ask is to find the concavity. When is it concave up? When is it concave down? Well, as you can kind of see from the graph, it looks like a U shape here and an upside down U here. So, as it turns out, it is concave up when y is less than L over 2, and down when y is greater than L over 2. So these two relationships, max dy over dt, equals when y is equal to L over 2, and then this concavity relationship are the two main relationships you need to know. This can show up on an MCQ or an FRQ. You'll always get one logistic differential equation, as it is with all of these sub-topics for just BC. You'll get one of these per test, and if it is on a FRQ, you will very often have to work with it through the whole FRQ, or through most of the FRQ. You have to know these relationships for the FRQ. And if you're working with it on the MCQ, you just got to know about the carrying capacity. That is where it plateaus. So that was logistic differential equations. So what can we take away from this unit? Well, proportional means that there is a k involved. So you'll either have k over y, or you'll have ky, or you'll have k L minus y, or you'll have ky times L minus y. This is your logistic function. It will sometimes ask for that. It will sometimes say, which function models a logistic growth of y, and you will just pick the one that is in this kind of format. You need to know how to work with slope fields, because there will always be a slope field on the test, at least one. You need to know separation of variables. There will also always be a separation of variables on the test. And then for BC, Euler's method, again, all these sub-BC topics will be on the BC test at least once. And logistic equations. So this is a pretty small unit. All of these, at least these 4, will appear on the test at least once. You can get a question like this on the test. Not guaranteed, but these ones absolutely you need to know. So that is it for Unit 7 differential equations. Thanks for watching.